In this lesson, we'll cover logarithms. To start with, does f of x equals 2 to the x have an inverse? So that is this function here. The way to answer this is by asking, does it pass the horizontal line test? Well, every horizontal line that you draw, it only goes through the function once, or like down here, it doesn't go through anything. And this means, yes, it passes the horizontal line test. So this, in fact, does have an inverse. So the question is, well, what is it? To figure that out, I listed these points over here. I'm going to actually state what they are. Like here, this one, this is -1/2. This point is 0, 1. Let's see, this is 1, 2. And then we have 2, 4, as well as 3, 8. Which makes sense. If you put these numbers into this exponent, you get these y values back. Now, because this function has an inverse, we know several points on the graph. I mean, just a reminder, over here, these were x and y values, and the inverse function is the function that interchanges these two things. So therefore, if you want to graph the inverse function, you can take these coordinates and reverse them. So on the inverse, you'll have the points 1/2, -1. You'll have 1, 0, 2, 1, 4, 2, and 8, 3. So if you want to graph what the inverse of this function looks like, well, here are several points that you can use to figure this out. Let's graph them. So let's see, we have 1/2, -1. It's right here. We have 1, 0, 2, 1, 4, 2, and 8, 3. If you draw the equation that goes between these points, goes through them, we get a graph that looks like this. Now, because a function and its inverse have to be symmetric over the line y is equal to x, it must be that since this line, or this function, is getting really close to the x-axis, this has to get really close to the y-axis. So to state a couple of facts, if you recall, on this exponential function, it had a horizontal asymptote, and that was y is equal to 0. Well, on the inverse function, there's a vertical asymptote, which is x is equal to 0. So we know a lot about what this inverse function is. We just don't have a formula for it. Let's state a couple of other facts. On the original function, the domain is all real numbers, and that's because it goes forever from the left to the right. But the y values go from 0 to infinity, so the range is from 0 to infinity. Well, on the inverse function, these are switched because we're changing the x's and the y's. In fact, the domain of this function is from 0 to infinity. So for my inverse, the domain is from 0 to infinity, but the range is all real numbers. The graph is increasing forever. Here it drops down, goes to -infinity. So that's the range. So these are things about the original function, and these are all things about the inverse function. All right, so what's the formula for the inverse? I mean, we have a graph, we have some facts about it, but what's like the actual equation? That is, what is f inverse of x? Well, no surprise, we call the inverse of an exponential function a logarithm. So that's what a logarithm is. It's the inverse of an exponential. We use the letters log to stand for log. To use function notation, we put a parentheses with an x to indicate that we're talking about this function. But we include one more thing. Here I chose 2 to the x, and this was the inverse for 2 to the x. If I used 3 to the x or 5 to the x, we would have a different function, so therefore we'd have a different inverse. For this reason, we put a subscript after the log to indicate what exponential function we are referring to. So when you see this notation, log base 2, what we were saying is you're taking the inverse of 2 to the x, this particular exponential function. So just to reiterate, a logarithmic function is the inverse of an exponential function. And right here we have a very formal definition for what this means. So on this side we have an exponential function. You have a base, you put a number into the exponent, and you get a y value back. So an x goes to a y, an exponential function. This means the same thing as log base b. We're saying we're taking the inverse of this particular exponential function. But in this case, the y value goes in and the x value comes out. So this statement and this statement are in fact equivalent. So maybe just to work with this definition a little bit, just to make sure we understand what it means, I'm going to write something that looks like this, like maybe, what did we have on the last slide? Something like 2 cubed is equal to 8. That is definitely a true statement. You cube 2 and you get 8 back. But here the 3 is the x and the 8 is the y. You can translate this into a statement about logarithms. You would say this is equivalent to log, well here we're talking about 2 as the base, so it's got to be log base 2. But we're putting 8 into the logarithm, and the thing that you get back is 3. So in the exponential side, 3 went to 8. But when you think of it as an inverse, it's the 8 that goes back to the 3. So this is really a notation only. In example 1, let's get some practice computing logarithms. So we just did this one on the previous slide. This is log base 2 of 8. But just to reiterate how this works, what we're looking for here is you start with the base. The base is 2. And maybe I'll call this value x. What we're trying to figure out is what number do I put into the exponent of the base so that I get 8 back? And well, from here I can think about a number that works. I happen to know that 2 cubed is equal to 8, so therefore x must be equal to 3. So the answer to this is log base 2 of 8 is 3. And the reason is because if you put 3 in the exponent of 2, you get 8 back. Here, let's try this here. Log base 3 of 9. Again, I'll call it x. You can just try to think about the number that makes it true. There's nothing wrong with that. But what we want to know is 3 to what power is equal to 9? Well, I know that 3 squared is 9, and therefore the number must be equal to 2. So log base 3 of 9 is 2, because if you square 3, you get 9. What about this one, though? Log base 2 of 1/4. What is this equal to? So this is going to be the base 2 to some number is equal to 1/4. Anytime that you see a fraction and you're dealing with logarithms, it's helpful to think of negative numbers. And the reason for this is in exponents, they make things into a fraction. So here's my thought process when I look at this. I see a 2 here, and over here I see a 4. And I know if I square 2, I get 4. But the problem is the 4 is not in the numerator, it is in the denominator. What this means is you don't want to just square 2, but you want to make it negative. And the reason for this is the negative exponent by definition means you do 1 over 2 to the positive 2. But if you square the 2 that's in the denominator, it actually gives you 1/4. So if you see a fraction, still look at this number and try to think of an integer that works, but then just make that integer negative. So here the answer is -2. And here, what about this one? Log base 2 of 0.5. So if we want to figure this one out, okay, so it's 2 to a certain power is equal to a decimal. Well, maybe converting this decimal into a fraction would be helpful. So this is really 2 to the half. Okay, I see a fraction, so I'm immediately thinking negative number. I think 2 to the -1 will work. And the reason is we take that 2 and put it into the denominator. And that leaves us with a half or 0.5. Therefore, the answer to this is -1. Try a few more here. What about log base 3 of 1 over 27? What's this? Well, 3 to some number should equal 1 over 27. Hopefully we can guess the answer. And, okay, I'm seeing it's a fraction, so I'm thinking it's got to be negative something. So, all right, you could just start by thinking about, well, what integers could work? Well, it's not 2 because 3 squared is 9. But if you try 3 cubed is 27. So this should work. 3 to the negative 3 is 1 over 3 to the positive 3. And 3 cubed is 27. And therefore, the answer over here is negative 3. Okay, what about log base 5 of 625? What's this? Okay, let's see. That's 5 to some power should be 625. It's got to be a positive number, which is good. So I'm just going to, try some numbers in my calculator. Like, all right, 5 cubed is 125, so it's not 3. 5 to the 4th is 625. It's got to hopefully be some integer that works. And after just a little trial and error, I put 4 in the exponent for 5, and it gave me 625 back, and therefore my answer is 4. What about log base 10 of 1,000? Okay, 10 to some exponent is 1,000. Okay, it's got to be positive. Actually, here's the nice thing about 10. If you square, cube, or raise 10 to the 5th power, what it will do is just add that number of zeros after the 1. So like if you square 10, you get 100, which gives you 2 zeros. Using that fact, I know that 10 to the power of 3 is 1,000. Essentially, the exponent is telling you how many times do you move the decimal point after the 1. Well, all that being said, that tells me that the answer is 3. 10 is very nice to work with when you're dealing with exponents. And for this reason, like on your calculator, you probably notice that there's just an log, a log button. So I'll just add a definition down here that if you see just log, by definition, we're talking about a log base 10. So this is such a common logarithm that we just shorten the notation because it's used so much. So you'll see this on most calculators. Well, that being said, what is log of 0.001? Okay, if I want to figure out what this is equal to, call it x. Okay, that's 10 to some x is equal to 0.001. Okay, this is basically a fraction just expressed as a decimal, so I know the answer is going to be negative. And if we use this idea of moving the decimal point, we're moving it 1, 2, 3 places, but this time to the left instead of the right. You can check this on a calculator, but 10 to the negative 3 is equal to 0.001. And the reason for this is 10 to the negative 3 is equal to 1 over 10 cubed, which is 1 over 1,000. That's a thousandth. So that's your tenths, hundredths, thousandths place. So here our answer is negative 3. And this, you can actually check on a calculator to see if your answer is correct. All right, let's try a few others here. Let's see. Log base 9 of 9 squared. What's that? Okay. Well, the way this one looks strange, but the way this works is you take the base, which is 9, and you're asking, well, what number do I put into the exponent so it gives me, well, I wrote it as 9 squared, but, this whole thing here, which I'll just copy down and put here. Now, written this way, where this side has a 9 to the power of 2, it actually makes this equation extremely easy to solve because, well, there's only one answer, and if I put a 2 here, we have made the left and the right side look exactly the same. So that is, well, you're trying to solve this equation, it's got to be that the number 2 for x is the only thing that will work. And for this reason, the answer is 2. So here's a nice takeaway. If you have the base, some number like 9, and it appears within the logarithm to that number, the answer is actually just the exponent. Like, will that work again down here? Log base 9 of 9 to the 5th. Using that logic, I'm thinking the answer is 5. I'll call it x for now, but let's see if this works. I take the base. I have to put a number into the exponent so that I get 9 to the 5th back. Well, clearly, looking at it this way, yeah, it's got to be 9 to the 5th. That equals 9 to the 5th, and therefore x is equal to 5. Well, something like this. Log base 4 of the square root of 4. This one looks strange too, but one thing to point out is, okay, here I have 4, and I'm seeing that's the base, which is also within the logarithm. So I'll call this x. 4 to some power should equal the square root of 4. And, well, really, square root of 4 is 2. What number would I put into the exponent that would make this thing a true statement? And here the answer is a fraction. So 4 to the 1/2 power, by definition, means take the square root of 4. And for this reason, the answer is a half. So if you see a square root, that means it's an exponent of 1/2. So for this next one here, log base 7 of the square root of 7, I think it should also be a half, but let's just check this out. Okay, so the base is 7, and what number will give me the square root of 7 back? Well, by definition, an exponent of 1/2 means take the square root of 7, and therefore the answer is also a half. Another logarithm that is used often is called the natural log of x, which is denoted ln. So this is called the natural log, or natural logarithm. So that's really an L and then an N. So that's not an I, that's an L. But anyways, you see the natural log of x, and what we mean is a logarithm whose base is e. And just a reminder, e is the number 2.71828, and it goes on forever. But let's get some practice with this logarithm. For example, what's the natural log of e squared? What is this thing equal to? Well, I guess first I'll rewrite this so it's really log base e of e squared is equal to some number x. And from here we can say, okay, well, I'll take the base. I want to put a number into the exponent so that I get e squared back. And the number that works for x is if you put 2 in place of it. So I know here that x is equal to 2. This looks different only because I don't actually see the base over here, but here the base is e, and inside we have that base, the number of 2. This is why the answer is 2. So likewise, down here, I'm expecting the answer to be 5 because this is really a log base e. But, just to be careful here, I'll call it x. Maybe I'll re-express this as log base e of e to the 5th. What does that equal? I would take the base and ask what number do I put in the exponent so I get e to the 5th back. And, well, that number's got to be 5. And therefore, x is 5. Now, what about e to the natural log of 5? What is that equal to? So I'll call this x. This is backwards. All the ones we've done up to this point were the logarithm with the exponent inside the logarithm. Here, the logarithm is inside the exponent. How can we figure this out? Well, what we're going to do is we're going to change this from an exponential equation to a logarithmic equation. So that means I'll write down the logarithm, which is the natural log. Okay, the thing that goes inside the logarithm, well, here x is the output, and over here it's going to be the input. And on the other side of my equation, well, the natural log of 5 is the input, so over here it becomes the output. So it's the natural log of 5. And what we want is a number for x that makes this equation true. And if I put a 5 here, I've made a true statement. The natural log of 5 is equal to the natural log of 5. Therefore, x must be equal to 5. We can try this again down here. Okay, what number is e to the natural log of 10? Okay, to re-express this from an exponential to a logarithmic equation, I write down the natural log. Here, this is the output, so now it becomes the input on the inverse. And the input over here is the natural log of 10, so I'll go on this side. The number that makes this equation true is 10. If you put 10 in place of x, you get that the natural log of 10 is equal to the natural log of 10, so x is equal to 10. And for the last example, what I'd like to do is graph this logarithmic function, log base 2 of x plus 4. We'll determine any asymptotes as well as state the domain and range. What I have here in red, this is the graph of y is equal to the log base 2 of x. This was the function that we graphed on the very first slide in this lesson. And what we stated was, well, there's a vertical asymptote at x is equal to 0. The domain is from 0 to positive infinity, and the range is from negative infinity to positive infinity. How will this function be different? Let's use transformations to answer this. The difference is we're changing the x values. Here it's an x, up here it's an x plus 4. Since we're changing an x, it's going to be the opposite effect. We're not going to go right 4, but I'm looking at this thing, and we're actually going to go left. So I'm going to start by thinking about, well, where does the asymptote go if we're moving everything left 4? From that, maybe I'll pick a couple of points and move those as well. And the last thing we'll do is figure out the domain and range. Well, if x equals 0 is the vertical asymptote, and we move it 1, 2, 3, 4 places to the left, probably no surprise that it's now at x is equal to negative 4. So I'll put that in here like this. Here is the vertical asymptote. Now let's move a couple of points. Let's see, maybe this one, that's the point 1, 0. And maybe this point here, this is the point 4, 2. If I move those 4 places to the left, this one goes here, that's negative 3, 0. And this one, if I move it 4 places to the left, is right here, that's at 0, 2. The function now must go between these points, but also approach the vertical asymptote and then increase like this. So I'm just sketching this by hand. It's not going to be perfect, but I'm expecting something that looks like this. So from here, I can see what the domain is. The domain is not from 0 to infinity, but it's from negative 4 to infinity. So on this function, the domain is from negative 4 to infinity. And the range did not change. It is still from negative infinity to positive infinity.